Yo, what is up, guys? Welcome back. Episode, I think like 71 or something. Got a little hot chocolate here, man. Gonna pump out some problems and some water. Yeah. So, we're gonna start with our problem of the day. Sorry, our Pokemon of the day. We got a Victory Bell. Let's take a look at the sound. Let's take a look at this 3-second one. Oh, what an interesting sound. It's like someone's screaming. Got some brilliant chess moves. Ah! Ah! Trying to do my highest, like, Ah! Ah! What is this? Voice all the original Pokemon. Ah! Ah! That's how Pokemon sound of the day. But yeah, let's take a look at our problem. Let's take a look at our problem of the day. Doesn't look too bad. Okay. Given an array of nums consisting of positive integers, we call a subarray nums nice if the bitwise and every pair of elements that are in different positions in the subarray is equal to 0. Return the length of the longest nice subarray. Subarray is contiguous. A subarray is a contiguous part of an array. Note that there is a length one always considered nice. Is this a sliding window problem? Okay. My intuition is sliding window here. I don't really know bit manipulation that well. But, okay. Let's do our sliding window here. Like nums. We can... Ow. Well, obviously we need a res array. So we need to, a res integer, so we can return that. We need a left. Okay, so how would we calculate this? Well, okay, so if... Well, I guess we have to start from 1, right? Because our edge case is, well, if the length of nums is equal to 1, are always considered nice. So I guess we would return 1. I don't know. I think that's considered nice. Note that subarrays of length 1 are always considered nice. Okay, so this hot chocolate's really good, man. Gotta respond to this text. Ooh. Okay, so I'm trying to think here. What's this meant to be? Just return 1. Trying to think here, like. Long as I subarray in 3848, the subarray. Man, that hot chocolate was good, bro. Okay. The bitwise and the bitwise and. So are we doing 1 3 3 8 or are we doing 1 3 1 8 1 48? 3 8 3 48 8 48 0. Both hints are completely useless. I'm curious. I don't know. 2100 longest nice subarray. Is this a problem? Pairwise disjoint bits. For any two numbers in the subarray, their bitwise and should be 0. Oh. Not nice, not nice. Eight 48. Have pairwise disjoint bit. We check 1 and 1. Okay. From what I'm getting here is that we do, well... Okay, so if left bitwise and in Python. Okay, if left and if num's left and num's right equal oh, sorry, we need to do a bitwise and, so it'd be if num's left and num's right equal to 0. But we don't need, we can start 0 0. If 1 and 1, 1 2. I think this has to be a while, maybe. Maybe it has to be because we can't increase our left pointer. Okay, let's check out the Leetcode video. Oh my gosh. I actually got recommended it this morning.
Hey everyone, welcome back, and let's write some more Leetcode today.
It's not on.
Let's solve the
Nice,
problem,
bro.
longest nice subarray. And I would say this is a pretty nice problem. We get a chance to go back to some of the basics But probably the most important thing with problems like these is making the most correct observations in order to figure out what those basics actually are. When I say basics, I mostly just mean like which pattern does this problem fall into. Once you know the pattern, then it's kind of just about filling in the little holes of how this problem, or rather how this pattern, can be used to solve the problem. And to fill in those like little holes, you kind of have to make those observations and really focus on the problem. So with that out of the way, imagine we're given an array of integers like this. And we care about the binary representation of each of these numbers. So just to make that easy for us so we don't make mistakes, I've kind of made a table for each number down here. And I think this really makes it easy. If you were given a problem like this one and you had no idea how to solve it, you have no idea what observations to make, at the very least, you could make it a little bit easier on yourself and just draw out the binary representations of a few integers and then use that to see if there's anything we can notice about the problem. But anyways, let's first read the problem, which is we're given these integers. We want to find the longest nice subarray that we can, and that's going to be a contiguous subarray. We want to return the length of it once we have determined what that nice subarray is, the longest one. And we're going to do this by being given some positive integers. A nice subarray is going to be defined as one. This is an example of a nice subarray, 3 and 8, because when you take 3 and you bitwise AND it with the number 8, take a look at the binary representation of those numbers over here. We see we have a couple ones with 3, and we have a single one over here with 8. When we bitwise AND these, that's one of the major operations about this problem, but there's a couple other bit manipulation operations we're going to need as well. And I'll show you those in just a sec. But for 3 and 8, when you bitwise AND, you check if both of the bits are set in that position. And clearly, we see that both of the bits for any of these integers are not going to be set. Meaning, in this case, I guess the word that I'm going to use for these two numbers is to say that they are non-overlapping. They do not overlap. The binary representation of these numbers does not overlap. And that gets to what this problem is really asking for. It's saying that a nice subarray is one that's defined just like this one, where when you AND every element together, the result should be a big fat 0. And now that you know what a non-overlapping or a nice subarray is in this case, let's look at the opposite, one that is not very nice, and that would be this one, where we have 1 and 3. This is definitely not a nice subarray, because when you bitwise AND these two together, you see that these two bits are different, but these two bits are the same. If you take 1 and AND it with 3, the result you're going to get is actually 1. In binary, it would look like this, 0, 0, 1, because that was a spot where both bits were set. Thus, the bit is going to be set in the output because of that. So again, in a more simple way, we could really just say we're looking for numbers that are non-overlapping in a sense. That's how I think of it to simplify this problem, because that long description of making sure the bitwise ANDs result in a subarray of 0 is a bit less straightforward and a bit less like human understandable. So I'm just trying to make it easy for myself. Now that we have that, now that we kind of know the trick behind this, like that was the key observation in this case, how do we go about solving a problem like this one? Well, the brute force would be a roughly n-squared solution where we look at every single subarray and just check if the bitwise AND of that subarray is equal to 0. And as long as it's true, we are good. But if it's not, then it's not going to work anymore. Like if we got to this point, for example, we realize that this is not a good subarray. Well, we can't really continue any further. I guess we could if we wanted to, but if this is not a good subarray, like if these two overlap, well, adding more elements isn't going to change that. These two guys still overlap. So what we would do in that case is, well, just start at the next element over here. Let me find the longest subarray I can from here. And then I would go to this element. Okay, I get that. And so far, so good. I look at the next element. I get that. And I think so far, so good. And then we keep going. And I think the next element will not allow us to maintain the non-overlapping property. It looks like this one does overlap over here. So then we would stop, and once again, we would start over. We would start at the next element, and from here, what's the longest subarray I can get? Okay, here, I got this, and now I got 48. These are not overlapping, and then I get the 10. It looks like the 10 is overlapping with the 8, so again, I would stop. Now, that's the brute force. I went through it a little bit longer than I do most times because I want the observation to at least make sense to you. Like, I'm not just pulling this out of nowhere. I think this problem makes it pretty obvious what the pattern is. The pattern is clearly a sliding window. Why should we have to start all over again? Why should I have to, if I started from 3 and I went all the way here and I say, okay, this is no good, and then I want to start at 8, why should I have to recreate this subarray over here when instead, when I'm over here, I can instead remove this guy, aka just slide my window. So that's the idea. I'll do a brief dry run right now, but I also want to mention that if you're new to this pattern, it's not trivial. You can't expect to watch like a 5-minute video and then just completely understand this pattern and understand how to solve difficult problems using this pattern. It's not that easy. I highly, highly recommend if you're a beginner to consider at least checking out Leetcode.io. It's intentionally designed just for people like you, so that once you kind of learn the patterns, I think the sliding window pattern is in this course, but once you learn the patterns, it gets a lot easier. And there's plenty of resources you can use to do that. If you want to use Leetcode.io, that's great. You could also use other resources as well. So now I'm going to go ahead and do a pretty basic dry run. What I usually do is initialize my 2 pointers at the first element. The main thing we're going to track here is the current bits that are set. So this cur is going to be a number, and it's going to be the binary representation of the bits that are currently set. So initially we can just say 0 because none of the bits are set. Then as the algorithm goes, the right pointer is going to be the one that iterates at each step. At each step, we're going to take this and increment it by 1 and move it to the next element. We're going to increase our window. So we look at the first element. We want to know, does this overlap with any other element in the current window? To figure that out, all we have to do is take our current window, like this should be the current window, and AND it with this, which is 1, and if this is non-zero, if this does not equal 0, that means that the window is invalid. But right now it equals 0 because we have 0 ANDed with 1, and the result of that is going to be 0. They're not both 1. So far so good. I mean, if you AND anything with 0, you wouldn't expect to get a non-zero.
Okay. Cur is equal to 0. Okay, for right in cur, if cur bitwise and right does not equal 0, so cur is equal to 0. How do we reset our counter? If it doesn't, then we... If it doesn't, then what do? Do our res is equal to... Calculate our length is equal to right minus left plus 1. Calculate window size, and then we update our res pointer and make res is equal to the max of res length. Then we return our res.
Result. So current ANDed with 1 is 0. So we are good. So what we do is say, okay, this window is valid. It's a window of length 1, and thus we can go ahead and just keep the left pointer here and increment our right pointer. I'll just scribble that out and move it over here now. Notice that our current is still 0, but we don't want it to be 0 at this point. So this is where it gets a little bit tricky. This is where we actually don't use the bitwise AND operator to update our current window, because as you can see, if we start with 0, then we can't ever set any of the bits in here. I mean, we can't do that with an AND operation.
That's the reason why I didn't write, because we're not using bits.
Operation that we can do, a bitwise, it's not exclusive OR, it's actually just bitwise OR to set a bit. So it's pretty much that simple. If you don't know what OR is, it's kind of the opposite. So if we had like 0, 0 and 0, 1, something like that, we only need a single bit to be set in a column to get a 1 in the output, and if nothing is set, then we still get a 0. So basically, like any bits that are set in this number will be moved here. And they definitely shouldn't be overlapping, so that doesn't really matter. So we can assume that we'll have a way to update cur. So now cur will be 1. And next, our right pointer is clearly at 3. So once again, we will take cur, which is 1 right now, and do 1 ANDed with 3. And we definitely will see some overlap. It is not going to be 0. That's bad. So what do? Things get interesting here. Now is the part where it's invalid, so we will shrink our window. We're going to make it smaller by shifting the left element. So what we're going to do is, while this is the case, while take 3 and AND it with cur, not just 1, but cur, we are going to shift the left pointer. So we can easily shift the left pointer. That's the easy part. Just move it over here. But there's something you want to do before you shift the left pointer, because now our window is just 3. Before we shift the left pointer, we want to unset this element. So now the question is, how do you unset a bit? Well, let's think about this for a second. I'll try to briefly explain it. So imagine over here, you have a number. Let's say our cur looks something like this. I have cur, and I'm just going to draw some random digits here. This is my cur. I have a new element. The current number that I'm looking at index I, maybe it looks like this. It's 0, 0, 0, and then it ends with a 1, 0. Or something like this, where this is clearly overlapping. So this is the new number, and this was our previous cur. So we can see there is some overlap, and we want to now take the leftmost element that was in our window and remove it. So essentially what we're saying here is we want to make room for this bit, which is overlapping with this one. So what our algorithm is going to do is just keep shifting the left pointer until this bit is available. Now, if I had a number, let's say my leftmost number at my left pointer looked like this. It was the exact one that we want to remove. It's just a 1, so it removes this bit. So how do we do that removal? Well, it's actually just the XOR operator, exclusive OR. We used OR to actually set the bits, but exclusive OR is useful for unsetting bits, and the reason for that is this. Right now, we have this number down here that I drew in red. We only want to unset this bit over here. We don't want to affect any of these. So you might say that, well, can't we just use an AND operator and between these two, or do some kind of inverse AND? Maybe there is like a way that you could make that work, but XOR is just a lot better, because exclusive OR means that if I do an exclusive OR with this and this element, then I'm just going to look at every number, and if they're different, I'm going to put a 1 in the output. If they're the same, then I get a 0 in the output. So you can see how, like, everything here that's a 0 means that we're just going to copy all of the bits that are over here. Zeros will not change anything. Basically, the property is this. If you take x, some number, let's call it n, I guess, n, and XOR it with a 0, the result is always going to be 0. That's an XOR property. So that's the reason why we do XOR. And also, I want to make it clear from this picture why we are going to shift the left pointer before we take the rightmost element that we just saw and add it here. Because you can see what I had initially, this is my cur. This is the new element I'm trying to add, but it overlaps with our current window. So what I want to do before I AND this here, before I set the bits here rather, I want to make sure I unset the bits first. If I set the bits and I put a 1 here and a 1 here, then I'm going to do the unsetting here, and I'm going to end up with a 0 over here. That's not what I want. So that's another key thing about this problem, and I think that's pretty much it. Once you know that, you can pretty efficiently solve this problem. So right now, our window is here. We haven't yet added the 3 to cur, but we recognize that cur and the current element 3, let's use a different color, cur and 3 is not equal to 0. So we will take the left element, this one, and XOR it with cur, which will bring us back down to 0, I think. And then we will see that, okay, now we can take this element and add it to the window, because now they are non-overlapping, and our window will become this. Then we will start expanding the window.
Can't you just make cur 0?
We'll get 48.
I don't know.
And
Like
so far we'll be good. We'll try to add 10. It won't work. Then we'll start shrinking the window. So we'll get rid of 3. And then this is what our window will be. You can see that there is still some overlapping here. So we will have to get rid of the 8. Then we will have these 2 elements remaining. They do not overlap. So this is our final window, and then we would be done. This is a linear time solution, constant space. Let's code it up. Okay, so let's just initialize the variables first. I'm going to have that, and then I'm going to have my left pointer, which I will set to 0, and then I'll have my right pointer going through the loop, going through every position in the array, and of course, we will have our current window, I guess you could call it, but probably the more appropriate and common name for this is the bit mask. Basically like an integer where each bit is going to represent something. You might be tempted to do something like this, cur anded with the current number, but remember, before you do this, we have to check if the window is valid. We have to do the other thing before we do that. And actually, we're never going to be doing current and that. That's not going to update cur the way we want to. We're going to be doing or instead. But anyways, we're going to check while this number is non-zero. While this is non-zero, what we want to do is, of course, update the left pointer, increment that. But before
got to add nums right here. Whoops. Oh my gosh, dude. So many people messaging me, bro. What are we doing here? Wildcard and
Before you do that, very important, update your current number, unset the bits that are set by the number.
Currency. Wildcard does not equal 0. Cur is equal to cur.
At the left pointer by doing this. After you're done with that, we can pretty much safely assume that our window is 0. And at that point, we can potentially update our result like this. Result is equal to the max of the current length and the length of the current window, which is right minus left plus 1. And after, don't forget to actually set the bits with the current number now. Because now we know for sure that cur ANDed with this number is in fact 0. By executing this loop, we did that. So to set the bits, it's pretty easy. You could do this cur or with the number at index r. So or is used to set bits generally. And just to quickly run this now, you can see here it works. It's very the number at
I wonder if this 0 works. I'm curious. Cur is equal to cur. Whoops, right. There's probably gonna be some edge case here. This doesn't work. Yeah. Cur is equal to cur. I think this is a Zor. Zor. Interesting. I think I was pretty close to that problem. I mean, the only thing I didn't really get was this is all right here. And then obviously this all. Let's recheck here. While cur num's right does not equal 0. Let's see what one. We calculate our length, we update our res, and then we all. Interesting problem. Not too hard of a problem. I feel like just the bit masking is just something that I struggle with, but I mean, definitely need to get to more problems with that, but $50 badge, bro. No way. Congratulations, 50 days badge 2025. Solving problems 50 plus days in 2025. Let's go, dude. Let's save this image, bro. Goated. Let's go. Thank you, bro. You for the medal. Do I get that on my profile, dude? No way, bro. I don't get it on my profile, dude. That's toxic. All right. Nice. Let's take a look at some more problems. It was a bit of a slow problem. I mean, well, it took 15 minutes or so, but always got to start off slow, but that's okay. Let's take a look at a powerful study program. Ooh. Take a look at another tree problem. Because we love trees. We love trees, man. Symmetric tree. Let's count our complete tree nodes, because why not? Oh, we already did this one. Let's reset it though, because we don't know. According to Wikipedia, every level except possibly the last is completely filled in a complete binary tree. Okay, yeah, I remember this one. And all the nodes in the last level are as far left as possible. If it can have between 1 and 2 H nodes, because of the last level. Design an algorithm that runs on less than omega. Alright, let's skip that one. What about a symmetric tree? Check whether it's a mirror of itself, i.e. symmetric around its center. Can you solve it both recursively and iteratively? Okay. Let's try and solve this. Let's try and solve it both ways, because, you know, we're a dog. So I'm thinking. So I'm thinking the iterative solution is definitely a BFS solution. Is it? I think you can do both, maybe, but. Okay, if we solve this recursively, we went node dot left, node dot right, we make them the same. If node dot left is equal to node dot right. Now I don't know how to do them either recursively or iteratively. I'm trying to think. If we did this in BFS, we'd have to keep track of. If we did this with BFS, we'd have to keep track of their levels somehow. I'm going to try a BFS approach here. I feel like this is kind of my intuition here. Q is equal to DQ. We want to pass in our root, right? Maybe we want something else as well. Our depth. and 1, because 1's our depth, right? Length is equal to Q, sorry, the length of Q, right? And we want to loop with a for loop, so we do for I in node is equal to stack.pop. Sorry, q.pop left. Okay, wait, node depth is equal to q.pop left. Okay, so if node.left, we want to do stack.append node.left and depth plus 1. Node.right. Sorry, q.append node.right depth plus 1. Okay. Yeah. We want to return true, right? That's going to be our case where we're just going to return true, right? So we loop through and we check, well, maybe we don't need to keep track of the depth, but we keep track of if it's left or right. Right? So because technically here, if they're the same, left would be 7, right would be 7. You know, the tree would be the same. So maybe we do it, because I was thinking about doing it with a hash map, but I think maybe with like a left and a right pointer, right? Or an integer or whatever. And then instead, when we pass in the depth, we pass in can we just pass in left and right like that? I don't know. Probably not. I guess we could pass in like a flag, right? Right, and we could pass in. I guess we can pass in true first. No, that won't work. How do we know that it's left and how do we know that it's right? Well, we could do the depth plus 1. Molecule length is equal to that in range length norms, no depth. Honestly, I really don't know how to keep track of this. Maybe. Oh man, backstretch. Jeez. Okay. Someone need to keep track of the level. So I think adding is the best way, but how can we add? Well, maybe instead of starting at the root, we can start at root dot left. Is that crazy? DQ root dot left, root dot right, depth. Our depth is 1. Right, because technically we start at left and right here, and we can compare that first. Then we can add a flag instead. So I guess our left is true and our right is false, right? So our flag. If flag is equal to true, we initiate our left and right values here. Left equals 0, right is equal to 0. If flag is equal to true, then we increment our left plus or equal to no dot value, right? Flag is equal to true. Flag is equal to true. And if flag is equal to false, then we just increment no dot val again. And then outside of this for, we compare, well, if oh my gosh, dude. If left does not equal right, then we return false. Otherwise, we get through this, we return true. Let's see if this runs. An integer is required, dude. What do you... Yes, if not root, return... I guess it's true, right? In a way. Yeah. Okay, Q is good. What? From collections import DQ. Is that what I had? Okay. Oh, okay. Forgot the extra bracket. That's why. Okay. Nums is not defined. Oh, whoops. linked here. True node has no attribute append. Oops, q.append, and then we want to append true because it's left. We want to append false because it's right. Yeah, double parenthesis here. Sorry guys, double parenthesis. Did that work? No, there's no attribute val. Non-type object has no attribute val. Or what? Non-type object has no attribute val. I don't know. I actually don't know the error, dude. Am I getting attribute error? Non-type object has no attribute val. Why do I have to check if it's null here? If I'm checking it over here. Okay, maybe it's because of this. I don't know. But I thought if I'm checking the root here, dude, if the root's null, then like, I don't know. It's right there. Let's just add. That's what I thought it was gonna be, but it just didn't really make sense to me. Okay, let's do, well, let's check in our code. Check right here. Well, if node is none, if not node, sorry, continue. Okay, maybe. Bro, how are we getting null values here, bro? I don't know what's wrong, dude. Several logical errors. So they're saying that we completely solved this incorrectly. Interesting. How? Oh, I didn't check this case. How was this false? Oh. Oh, I understand. I think that's the change the title from mirror tree to symmetric tree can cause. Okay. So we can get rid of this crap. Get rid of this crap. Alright, we're right here though by appending the left and right subtree. Right? We append root dot left. Alright, root dot right. Can get rid of this logic, right? Not return true, right? We create our queue. We iterate here. In range length. Our node flag is equal to q.pop left. Oh my god, dude. Okay, so if we want to check here, we'd have to check, well, Q to left. We don't want to append this shit. So I think really all we have to do is just this is, man, really confusing me. Okay. If no dot left and no dot right. Well, if we add the current node, so we've appended. Can we maybe pass in our root here? Pass in our root and we check, well, what is equal to above that? We check if no dot left. Otherwise, we just return true. See, this won't work with iterative because solve this. Okay. Here we want to append root dot left, root dot right. Okay, root dot left, root dot right. We do while q. We have to pop, so left to right. Is that how we? Oh. We want to make this one, not separate items. We want to make it one item. Root dot left, root dot right, left, right is equal to Q dot pop left, right? So we pop the left and the right and we check, well, we have to check if they're empty, right? If not left and not right, we continue. Okay, then we want to check, well, if left dot left is equal to right dot right, right, then we just want to return false. Otherwise we just want to check, well, if left dot left Q dot append, if left dot left, jeez, this is confusing, and I think right dot right, Q dot append, left dot left, right dot right. If left dot right and right dot left, Q dot append, left dot right, right dot left. What did I do wrong? If not left or not right or left of L. If not left or not right or left of val does not equal right of val. Sorry, I just kind of burped into the mic, my bad. Getting a little bit of a headache from this problem, dude. Jesus, expected 2, got 1. Oh my gosh, dude. I think this should be good. I think. Bro, Jesus, man. Oh, left, right, Q pop left. If not left and not right, continue. If not left or not right, or left of those, Q dot append, left dot left, right dot right, left dot right, right dot left, return true. The outside. Oh my gosh, dude. That's why, bro? Really? What did I have it as before? Oh, I didn't like this. Right, yeah, it didn't like that. It just wanted me to do it. So we're checking here. Ah, damn it, man. Left to right is equal to q dot pub left. What would the recursive function be? How can I think about this? Recursive function. 2, left, right, 3. Okay, let's do. I don't know if we're gonna implement DFS here. Sorry. Left, right, right. When we implemented our function here, we DFS root dot left, root dot right, right. We loop through this and we check, well, if not right or left dot val does not equal right dot val, then we return false here, right? False. If left dot val is equal to right dot val, we return true. Otherwise, we return left dot val is equal to right dot val. Right. No. Okay. So apparently we need to check if they're not null. So if not node, Sorry, if not left. Alright, empty. This is technically true. Otherwise, we need to return the mirrored, so is mirror. Sorry. DFS. This is not a DFS function, by the way, but probably change this. Let's change this to mirror. Mirror. I feel like this will confuse anyone that maybe skips to this part or something. Mirror. Left dot left. Right dot right. And mirror right dot left. Sorry. Left dot right. Right dot left. Jeez. If not left and not right. I don't think it really matters where I put this if statement, at least in my opinion. Maybe it does. Oh. Why does that matter though? That's really interesting. I don't know. I thought the if statement just wouldn't execute, like. Oh, okay. It's because we got ors here. That's why I didn't think about that. So we have ors here, so these could be true, right? But we're checking an and here, so this needs to be checked first. Alright, so this could execute incorrectly. I understand. Okay. Okay. That was a long ass tree problem. Again. Ow. Let's take a look at some more problems. Okay. I guess we do a couple problems out of Leetcode 75. Monthly $35 a month. Jeez. It's expensive, man. Okay. Asteroid collision. We already done these ones. What should we do? I kind of want to do. Let's finish the sliding window one right here. We've done this one before too. What did we do? This October 3rd. Given a binary array knobs and indicate return the max number of consecutive ones in an array if you can flip at most k zeros. understand why this is a sliding window problem. Okay, so I'm thinking we go, well, we just have to really keep track of zeros. So we keep moving, right? If there's a 0, we decrement, right? If we reach the k element in the count, then we save this and we move up one. Okay. This might not be too bad, but maybe not. I guess we'll see. Right in range length nums. Right. I want to create a few integers, so we create a left pointer. We want to obviously create a res array to store the longest stuff. We loop through, yes, while left is less, while, let's create like our count. We need a count variable too. Okay, so we do while our count is less than k, wait. While nums right is equal to 0 and our count is less than k, then we check, well, first of all, we added that k, so we do count plus equal to 1. If k is equal, so if count is equal to k, we have reached max zeros, right? So then we need to do something. We need to do, well, then we're just gonna need another while loop, but I don't want all these while loops. Okay. I'm gonna fix this up. I'm gonna use an if statement here. So well, if nums right is equal to 0 and our count is less than k, then obviously we want to increment our count. But then we want to check, well, if count is equal to k. Okay, now we do while count is equal to k. And while count is equal to k, okay, while our count is equal to k, left plus equal to 1. While count is equal to k, and then we increment left. That res, bro. Okay, so while count is equal to k, we increment our left pointer. Okay, then if our left, if num's left, should be I don't know how to do this part, dude. While left is not equal Well, count. So we get to here, right? Well, count is equal to k, which it is, and nums left does not equal 0. Then we increment, boom, 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 boom. Then we get to here. Our left pointer's here. False. And our right pointer's here. Two left. I don't think this is gonna work, but I'm gonna return the res anyway. Well, we're not updating our... Reason why we're not returning anything is because we're not updating our... I guess our count is equal to 1. Okay, well... Now we make count equal to 1. Do well, nums left does not equal 0. We increment left plus equal to 1. What is wrong with my sliding window here? Brr, 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 brr. We get to here, so we go to, then we're checking this one here, and that's when it goes, right? No. Getting pissed here, bro. Like, I know it's wrong, bro, but I just don't know how to do it. Like, I know that we're getting here, right? So we get to our second 0, right? Okay, we're equal to 0. Then we go and we find the closest 0, right? So we're at left here, right? And our next iteration, we're at 2 zeros, but technically it's 3. Instead of properly streaking the window where there are k zeros, it incorrectly resets counting going, which breaks the logic. The goal should be to remove left past the 0 to allow another flip, not to reset the count. Fuck, man, we were close. If I run range length, numbers right is equal to 0. Count plus equal to 1. While our count is greater than k, if nums left is equal to 0, that's equal to 1. Otherwise, we increment our left pointer. Easier way to do it. We update our max. Damn, bro. It's so frustrating, bro. I was so close, man. Like, so close. I was thinking about it the right way, but I just couldn't really execute this code properly. Like, damn, bro. Okay. I'm going to leave this one for tomorrow. Come back to it. Maybe let's do just a quick, simple one. This will probably take me 1 second, but September 16th. Okay. Given an array, return true if the number of characters each value of the array is unique or false. Otherwise. Okay, right. We're looking for the same number of occurrences. This is false because they have the same. Okay, so let's do a counter here of our array. Print our array. Then we loop through. Sorry, print my dictionary, not print array, bro. Brr, 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 brr. We got a counter here with all our values. And we want to check, well, for value in -dict.values, we could have like we can create a hashy here. The set could say, well, if value not in my dictionary, then we can just add it. Hashy.add value, right? Else, if it is, then we just want to return false. Otherwise, we can just return true for all other cases. Why? I think I'm getting confused with this problem here. We have 1113, 2. So we would go, well, what are we printing in the values? Three. Okay. Three, two, one. 1, 1. Yeah, okay. So oh my gosh, not in my dictionary, not in hashy, bro. I think that's what I did wrong. Value not in hashy, hashy.add value. Otherwise, we else here. If it is, we return false. Outside, we return true. Can't really remember, but I think I had this as my dictionary. Yeah, there you go. Nice. Optimal solution 2. Is that the optimal solution? I don't know. Okay, using hash map and set approach. Yeah. Maybe it's me. Okay. Nice. Okay. We're gonna call it there for the day. Appreciate you guys watching. We will jump back into it tomorrow and do some more problems. Let's just refresh our page, see what we got going here, what we got looking in the future. Yeah, I mean, got some of these left. I mean, this will probably take a few episodes. I think we'll be done with this week. The link list, that's pretty straightforward, I think, too. We got some ones we haven't done before, too, which is pretty cool. Like, then we get into binary tree DFS and BFS, binary tree, some ones we've already done. Then we get into some graphs. This is where we'll probably start our graph journey. Even though we have I think it's time that I think we're getting ready to get into graphs now, which is pretty exciting. I think I have a pretty solid foundation on DFS, BFS, and binary search trees and everything. I think decent. DP problems. Yeah, some graphs. Learn different graph traversals such as BFS and DFS. Learn minimum spanning trees and their different algorithms. Learn the shortest path and its algorithms. Learn topological sort and priority queue. Maybe instead of going into these problems first, we'll do the heap priority queue first chapter. We'll learn that, and then we'll go into these like graph ones, because I think probably this is important first. I mean, we have some binary search, some backtracking. Okay. These are the ones that I definitely need to get a little bit better at, for sure. But yeah, I mean, it's good progress. I'm feeling more confident. When approaching the problems, for sure. I'm getting close to solving the problems. Getting good intuition. So I'm pretty happy with where I'm at. So yeah, I will see you guys tomorrow. Thank you for watching.